Okay, so here's another tutorial for fluid mechanics. And for the project, it's not really all that much different from the previous one, but the other one, the previous one was using 2D. This is going to be 3D, and I'm just going to use the flow past a sphere for the example. All right, so I am starting out in, I'll start in millimeter units, so I click down there at the bottom. I'm going to make my background white. Hopefully make it white. It doesn't look white now. I guess it looks white. Okay. And I'm going to pick my front plane, and I'm going to make a sphere. So I'm going to make a ball, and I'm going to make it 50 millimeters. And then I am going to, actually, let me change that sketch. I'm going to give it the center line to the middle, because that helps me to rotate stuff. I think it was, and then features, and then we do revolve, and pick him, and actually I didn't need it. Okay, it was totally okay with it. Whoops, rebuild errors. I hate it when that happens. So let me clear that. No, didn't like it. Ugh, self-intersecting. Okay, so let me go back to the sketch, and I am going to, let's see, trim half of it, and I think you're going to be okay then, and then do the revolve. And I think it picked it. Yeah, it was okay with it. Cool. All right, so let's save this thing. And I guess I'll go sphere 2. Sphere 2, because I did this before. So sphere 2. And now we're going to make sure we're going to do the simulation. So I'm going to come up to this gear and use the arrow next to it, do the add-ons, and make sure that SolidWorks flow simulation, this right here, is on. And under tools, we're going to come and do, where'd you go? Did I just turn it off? No, there it is right there, flow simulation, all right? And we're going to go project and then wizard, right? So tools, flow simulation, project, wizard. And we're going to call this thing sphere drag. And configuration, those are all good. So we go next. And I'm going to use, I guess I'll use MG, SI units. And I can accept all these next things. We're going to have external flow, and I believe that this is going to be non-time dependent. Let me see. Pretty sure. Non-time dependent. And next, we're going to pick as our medium in this. I think we're going to pick either air or water. Right, what are we going to pick? Air or water? We decide we're going to have air. So we'll go gases, pick air, and hit add. And we're not going to do a high Mach number or humidity. And we're going to accept the defaults when it comes to the roughness. So we just want it smooth. And so here's where we're going to add in our velocity. And I really wish there was a means of controlling this defined by, no, okay. So in the X direction, we're going to start off with a velocity of 0.003 meters. So 0.003 meters per second. And the turbulence parameters, they're good to look at. I haven't changed any of them. So, but here's where we might change them, right? We might change the degree of turbulence intensity. And I'm looking for, and I haven't seen yet in this, in SolidWorks flow simulation, turbulence models and what they are, but they have to be some. So anyway, we'll hit finish, but we can make changes to all of these. They're going to be, we're going to see them here in a second. All right, so we pan out. We can see here is our computational domain, right? So they decided because it was an external domain that this was the box that we were going to put the thing around. And we might want to change the size of this box. They made that decision for us. And we could change it by going into anything in these trees right there, by the way. And you also note that we can make multiple analyses right here, but we're doing the one sphere drag down here. So what we want to do here is we want to set up some goals for ourselves. So the first goal that we want to try to do is we're going to set we want to set a global goal, right? So we insert a global goal, and let's make it a force. The force in the X direction, because we're going to do things based on drag. So we could have other ones, but that's going to be the one we're going to use for this analyses. And then we also want to set up a equation goal. And here's also another one where I wish we could maybe have a little bit more control and used variables instead, so we wouldn't have to edit this. But I don't know a way to do it. But we can in here write an expression, and we're gonna write the drag expression. So we take this right here, and you'll notice that we clicked on that, and it became a variable that we're including, and we're gonna solve for the drag coefficient. We're going to create the drag coefficient. So if you were looking at this, let's see, the equation that we're going to put in here. All right, let me tighten that down. The equation we're going to put in there is going to be the drag coefficient is going to be equal to that drag force that we just grabbed times 2 and divided by rho v squared and a, right? Which we also know to be, so we're going to write drag times 2 divided by the quantity rho, and then v squared, right? So that's like an input right there, and then it's going to be times pi, and then times r squared. Or we might go by the diameter, because we put the diameter in there. So I think we ought to put the diameter. Yeah, that's what I think. But anyway, so that's what I'm about to type out there. But it's looks like an equation here. So we go times 2 divided by the quantity, and I'm going to go ahead and follow along 1.204. times, now the velocity is 0.003 squared, and then times pi, which I'll go 3.142 is enough sig figs as far as I'm concerned. And then I'll go divided by 4, and then times 0.05, that's 50 millimeters, but in meters, squared. I believe I got that right. We're going to name this drag coefficient. And it's going to be non-dimensional, so we're going to cycle down here for the dimensions. And there's dimensionless LMA. I don't know what the LMA stands for. Least, mid, average, or I don't know, something. But this is for convergence control, right? So we need to have some amount of convergence, something as the measure of when something converges, or the dependence of it. So we're going to hit OK, and you'll see that that's up down there as a goal. And if I'm not mistaken, we might be ready to just hit solve. There's a certain amount of we might want to grab the global mesh, right? And look at, well, let's see, we'll go to the global mesh and hit edit definition. And it's on 3 right now. Let's try it. Let's move it to 4, right? And we might want to show the mesh. So we'll hit OK. And you might want to like go click on this and go show basic mesh, right? So that's sort of like, this is the coarse mesh that we've made onto it. But let's hit the run. So you come up here, up to there. Yeah, right click up on top of that sphere and hit run. And this might go really fast, but if it goes slow enough, we're going to be able to click on something where we can see the convergence, and we can also see the like an animation. It'll kind of give us an idea of what's taking place numerically. So we go run, and if we click on this window, and I think it might, yeah, I already had the settings in there, but if you needed them, you could click onto this right here to show the this graph below, or you can click onto this button right there, and it'll and tell it to show you velocity, and you can kind of see this numerical crunching at work, right? As it's taking a look, and it has 2 graphs. One is the drag coefficient, and you can kind of see, okay, it's finished. It says solver is finished at the bottom. So we can now, you'll see results. We can now expand this, and you'll see that it has these results. We can kind of get a better look at what has taken place. So there's lots of different ways that we can analyze this, but probably the easiest thing to do, the most informative, is to hit a cut plot. So we right click and hit insert a cut plot, and it already decided that it wanted to use the front plane, so that was good, but we could use a different plane, and we want it right on the center of the thing, right? So we want to look at it on a cut plane through there and see contours. You could also put vectors and other things. You could put both on there at the same time if you want. And you might want to change this to velocity. So we can go to velocity and extraction, or you could go total velocity. And let's go OK. And so there you go. It's probably, I already have some settings in here and it remembered them, but it's a good idea to modify this graph right here. And I wish I could remember how I modified the graph. You can pull it around and stuff, but I think if you right click on this graph, let's see. There's a bunch of different, there's some things on the graph that will allow it to be. I want to change the orientation. Can't remember how I do that. No, I want to, no, stop it. All right, so you're making me mad. All right, grab you. How come I can't grab you now? All right, so I'm gonna click over there, and now I'm gonna click over this one. Anyway, let's see. It's best to click on this thing, or you could click on any of them, right? You click on these little graph things, and you can get it to rotate into. But I think it's best to have it looking straight at the thing. Let's see. Can I change? Where's the thing where I can change? It's not letting me do this. It's being a pain. This is making for great video. I'll pause it. Okay, I think I figured it out. Yeah, if I can hover around it and get that, I can right-click it, and I can make it horizontal. I can stretch it out. Hover, there you go. I can also, I think you go to appearance, and plot names, reset to default. Let's see what happens if you do reset to the default. No, that's not what I wanted. Nope. Make horizontal. I like the horizontal better. And I want to control my contours. So let's see. Make vertical appearance, edit. There you go. All right. So you can change colors into the thing. You can change the number of increments, and I prefer to have like a nice even increment onto the thing. And you could also change the the maximum in there, right? 0.003 makes it kind of makes sense as being the maximum, at least for this one. And you can change out what these are. I also another thing I like to add and edit the definition is to put the vectors in there on top of it. It's not letting me do it. There it is. Put the vectors on top. Can't quite see them. There you go. You can see the vectors. Okay. I might want to improve what my solution is into here and refine it by taking a greater, a better grid. And but let's go ahead and see what our results are. So we want to try to find numeric results. So go to Surface Parameters and right-click in Insert. Seems to be slowing down here. And I'm going to go ahead and have all these parameters. I don't care. Well, I need to define a surface. I'll define that outer surface, right? And I also might want to get an output of my drag coefficient. Let's see that right there. Solve, run, tool, simulation, load, unload, using cut plots, blah, blah, blah. All right, so what we could do in this output is I can just export to Excel, and it'll export all this information. But the one that I care about is this X component of force. Right, so we have force, and here's the X component. And so maybe I could put this into a separate file here, but maybe I will just go ahead and write out do it here. We have a rho, mu, and diameter, and velocity. Right, let me double check. Let's see, anything else I need? I might go area anyway, right? So the row that I'm using for this is 1.204. At least that's what I thought I was using. Note over here that we have a density somewhere. The density. Yeah, okay, so that's what they were using in there. So if we want to go back and update what the computer was using, that's what we would do. We also have mu, so I could have... by the way, I could just go like this right here. If I could have, just to organize the thing like that right there. Okay, sure. And then equal, what's my mu? Is dynamic viscosity right there. Boom. The diameter, that I wanted 0.05, right? The velocity, it's weird that it doesn't show it here. I don't know why that is. But it does show surface area. But that's not the area that we want right here. So the velocity, we entered that as 0.003. And the area, we could just say is equal to pi divided by 4 times, times this diameter squared, right? So what we can get from that, we can get the Reynolds number, right, and equals, and let's say that it's going to be rho times the velocity times the diameter divided by the viscosity. Boom. So that's a pretty low value, 9.9. But so you can expect that to be a laminar. This is a laminar solution. And so we could also say that the drag coefficient, CD, is equal to, well, let's just say it's going to be equal to what we had just said before, right? It's going to be the drag force, that times 2 divided by the quantity of rho times velocity squared times pi, and then times area. Oh, I don't need pi. I already have area. So it's just times area. Boom. And we get a drag coefficient of 4.26. Okay, so it was interesting because this one I'm looking right here had a difference or was just a little bit of a different response. We could actually refine this. I would actually put this into a separate spreadsheet and solve the thing. But anyway, this was the additional options, right? We'll say that's okay right here, that we could do. We have several different things. One is we could refine the mesh. So we could come into here and we could put in, say, insert a local mesh. And we have a bunch of different ones that we can try out. But we don't have any channels because there's not any things that have like gaps between them, so don't do that. We can do like an advanced refinement and like pick a curvature level off of that and change it by the number of radians. That might be an interesting thing to use. What I found was pretty good was equidistant. Right, so I pick this surface right there, and I maybe I could improve the level of the thing. Right, and so maybe I'm going to go with 4 right here, and I'm just going to make it a small little thing. Let's see what happens. Go OK, and then do create mesh. Right click mesh and hit create mesh and run it. And it might bring up another little window up here as it tries to do that. And you got to be careful not to go too large because it might take like a long time and really bog down your system. So you have to be kind of like a little careful here not to go too ambitious too quickly. It says that it finished normally. Notice that it got rid of my results, right? It says it only has mesh only. But we could put this in here and we could look at the mesh plot. I'm not sure. Is that the right? No, I'm sorry. Let's go to under cut plots and insert. All right, so this would be a different one, and we just click on mesh. And so now you could see what the mesh refinement looked like, and that's it looks like it makes it better. We could run it and we can see what the effects are pretty easily. Run. We gotta be careful not to go too fine of a mesh, but like let it solve. And we want a new calculation. We want to be careful not to, when you do this, not to just run it over the old calculation if that's an option. But it should pop up a new one of these windows. Or is it the old window? No, it should pop up a new window. There you go. And with a refined mesh, it's going to be a slower solution. It's got more nodes and places to go. A good idea sometimes is to look at the shape of this contour and to maybe, if you were really looking to improve the thing, to, where the contour is representing where there's differences in velocity. And so where there's differences in velocity, you want to probably, make more grid points, or a finer grid in that region, or at least have points that contain there. You also notice that we have changes that are taking place outside of our domain, and therefore, we might consider wanting to extend our domain out further. This is like watching paint dry, so pause. Okay, so we finished, and it took, it says that it took the CPU to, it was 3 minutes and 18 seconds, compared to this other one took 32 seconds. So you can see what the consequence of the refinement on how much time it took. And we could go back and we could take a look at this this cut plot. And we might have improved it, but we don't know quite sure. We can instead edit this surface definition and hit that export to Excel again. Right, so if I did everything the same way, I could potentially just hit this copy and paste. Notably, I'm in cell H21. So H21, boom. And you can see, now we can kind of see what the differences are between that. Did we improve it, Al? Well, it's hard to say what's improvement, right? It is the Reynolds number remains the same. Of course, it would. But we could check for convergence. The problem with this problem, or one of the struggles we have with how slow it is because remember, this is three-dimensional. So when we, for instance, were to take a look at the mesh, right? We could let me hide this one. Or right click and hide. We hit right click and hit show. That's only showing us the cut right here. Like, we could actually move this out and we could kind of see, like, that is all the grids that are taking place. And so this three-dimensional, by making it the grid refined, we really increase the number of grid points. So it's really preferred to do a two-dimensional one if possible on things. It'll be a much quicker solution. But you might want to find out something that's 3 dimensions. So I'm not discouraging you from doing it. I'm just giving you a warning that when you go to do a 3-dimensional plot, you have the potential to really slow it down by making your grid too fine. But it is important to check and see what the effect of the grid mesh is. So this might have been too much of a grid refinement. We could try something a little bit less and make a couple different grid changes and see what happens. So anyway, this is the demo of a 3-dimensional one. I'm going to do probably another where I do an airfoil instead to try to show lift. So see you soon in another